The frequencies which arises between lower half power and higher half power will be the maximum frequency, which is called as a peak frequency, for which the maximum current as well as maximum voltage can be identified. There is certain amount of current which is flowing internally within the circuit, but exactly it doesn't derive any of the power from the source, which is known as weightless current. So this is also very important for 1 mark. In case of transformer is the one which is used to give a desired values of the alternating voltage, right? Is it like 100% efficient? No. Hello everyone, I am Vrinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 5 of chapter 7, Alternating Current. So in today's class, we are going to deal with the sharpness of the resonance curve, and next will be the weightless current, transformers, and the loss of energy in transformers. All these things will be studied today, and we will have to wind up with the alternating current chapter here. So first of all, let's deal with the sharpness of resonance, which means to say that there is a resonance curve with the help of, by taking LCR diagram, LCR circuits waveform diagram into an account, we will be getting the resonance, that is electrical resonance. It is given as this form. Okay, so this is the phase which gives you the omega, and this is the y-axis will give you the amplitude of current as well as voltage stuff. So now, sharpness of the resonance, you have a peak value which is given as omega naught. It doesn't depend on the R value, because of which for every peaks, all the peaks at certain instant of phase, it has got the highest amplitude, that is at omega naught, because it doesn't depend on R. So suppose if you consider this as the maximum value, call it as I max. So half of is, that is RMS value, root mean square value of it is I. Suppose if this is I divided by root 2, that means the maximum current, you are dividing this maximum current value whichever you have got here divided by root 2, which gives you the IRMS value. IRMS value of the current, root mean square value of the current, that is for the maximum current. So the peak point to which vertically it falls on the horizontal line, that is omega, which gives you the phase over which you have the omega naught. Omega naught is said to be the peak value where exactly the maximum current is been identified. So now if you just extend those values vertically to the IRMS value, then you have omega 1 and omega 2. This is called as lower half power frequency, and this term is known as upper half power frequency. So we have lower half power frequency as well as upper half power frequency, and the frequencies which arises between lower half power and higher half power will be the maximum frequency, which is called as a peak frequency, for which the maximum current as well as maximum voltage can be identified. So we can say that at resonance, XC will become equal to XL, which means to say 1 by omega naught C will be equal to omega naught L. So interchanging this, you have omega naught square is equal to 1 by LC. So omega naught, apply root for all these things over right hand side, so it becomes 1 by root LC. So this is the value at resonant frequency. The peak value at resonant frequency will be omega naught is equal to 1 by root LC. Okay, so having this concept, we are just going to deal with what happens to the power at maximum frequencies. Power equation is given by P is equal to I square into R. So at maximum value, that is maximum value of the current, I square, and this is maximum into R. Suppose if you consider RMS value of I max, then you have P dash is equal to I square RMS value, and this is maximum value what we consider. So RMS value is given by IRMS divided by root 2 into R is the value what you have for the power in case of half power frequency as well as the maximum frequencies. Okay, so this is the power value, and this is at resonance condition. The capacitive reactance will become equal to inductive reactance, for which we have given the peak value. So omega naught is equal to 1 by root LC is the value what you have. So in this we will have to define for the quality factor, that is QF, and bandwidth, as well as quality factor, bandwidth, half power frequency. So we have to give quality factor, bandwidth and half power frequency. So quality factor is nothing but the ratio of resonant frequency to the bandwidth. So the resonant frequency occurs here at the highest point. So the ratio of resonant frequency to the bandwidth is said to be the quality factor, whereas bandwidth in the sense the width between this place and this place. It's the differences between upper half frequency and lower half frequency. It's a difference between initial and final and initial frequency, which gives you the bandwidth. The width of this line gives you the bandwidth. Okay, so next you have half power frequency. Half power frequency means half of this main frequency. Half of the maximum frequency is said to be half power frequency, which we take as RMS value or the root mean square value. Okay, so bandwidth, it becomes 2 delta omega. That is because we have omega 1 can be termed as omega minus delta omega. Omega 2 can be termed as omega plus delta omega. So omega 2 minus omega 1 gives you omega plus delta omega of minus omega minus delta omega. So here we have plus omega cancels with minus omega. Delta omega minus into minus is plus. So it is delta omega plus delta omega gives you 2 delta omega is the value of the bandwidth what you have. So these are all the explanation for the quality factor, for the bandwidth, as well as half power frequency. And next, having this under the sharpness of resonance, we go with the powers in circuit. Powers in AC circuit, only the formula is very important for you to understand. That is cos phi is equal to R by Z for numericals. It is very important for numericals. So it goes like this. Cos phi is equal to R by Z. So phi is equal to cos inverse of R by Z. So Z is nothing but the impedance what we are talking about. So impedance value is, so it becomes phi is equal to cos inverse of R divided by root of R square plus XC minus XL the whole square. So you can write this as phi is equal to cos inverse of R divided by root of R, and then you have, since XC is equal to 1 by omega C and XL is equal to omega L, you can substitute here as plus, this is R square, 1 by omega C minus omega L the whole square. So this can be the value for power in AC circuit, which is considered as an important formula in order to help your numericals or help to attempt the numericals with this. Next is wattless current. What is meant by watt? Watt is the SI unit of a power. So wattless means powerless. So the current which derives no power, so without the power, presence of current is said to be wattless current, which means to say that there is certain amount of current which is flowing internally within the circuit, but exactly it doesn't derive any of the power from the source, which is known as wattless current. So this is also very important for 1 mark questions from this chapter. Okay, so now we are getting on to the transformers. What is meant by a transformer? Transformer is a device which converts the alternating voltages to a desired value. Okay, so transformers is the one which uses the alternating source which provides alternating voltage. So this alternating voltage, which changes its voltage every now and then, has to be given a constant value. So it's used to give a desired values of voltage with the help of this transformers. With the help of the transformers, we get the desired value of the alternating voltage is what we study here. So that is why the transformers are used. So here there is a core surrounding which there is windings of a wire. so which gives you the depiction of a transformer. So here the same thing can be represented here. There are coils over here, inductors, which induces EMF. Okay, so number of turns in this coil can be called as NP, which means to say this is a primary coil, and number of turns in this coil is called as NS, which means to say it is secondary coil. So the input is given over here, input is supplied here, and output is received from this end. So input is supplied to the primary end and output is received from the secondary end. When this is a case, what we have to do in the sense, we'll have to consider, according to Faraday's law, induced EMF can be given as minus n number of turns due to the change in flux with respect to time is what we have. So now Faraday's law says that it is for each and every individual coils what we consider. So first we consider for the secondary coil, that means output. What is the output? So it is minus ns, and ns means it is to say that it is number of turns in the secondary coil and flux through that coil. Okay, now due to the induced EMF in the secondary coil, it possesses certain reaction in the primary coil as well, which is called as a back EMF, and that back EMF in the primary coil can be called as epsilon P is equal to minus NP into d phi by dt is what we have. So this can be considered as equation 1, this can be considered as equation 2. Okay, so now the induced EMF, it can also be equated as voltage, that is if the applied voltage is considered to be Vs in case of secondary coil is equal to epsilon S and Vp is equal to epsilon P, then we have the set of equation turning out to be Vs is equal to minus Ns into d phi by dt and Vp is equal to minus Np into d phi by dt. Okay, so this can be equation 3 and this can be equation 4, which I'll be giving now. So now we have Vs is equal to minus Ns into d phi by dt, equation 3, and Vp is equal to minus Np into d phi by dt, equation 4. Divide equation 3 and 4, we have Vs, d phi dt cancels out, so we have Vs by Vp is equal to Ns by Np, where minus and minus division gives you plus, so this is one set of equation. So now we have, if Vs and Vp is equal to Ns and Np, if suppose this equation is said to be 100% efficient, that is the transformer is said to be 100% efficient, then the power value is V into I, so it becomes input power is equal to the output power. So on equating, Vs by Vp is equal to Ip by Is. So inverse of it, therefore Vs by Vp is equal to Ns by Np, which is equal to Ip by Is. So these both are directly proportional, whereas this is inversely proportional. Having this concept, we are just going on with the step up and step down transformer. So step up transformer, in the sense we have Vs by Vp. Okay, so suppose if Ns is greater than Np, that is number of secondary coil turnings is greater than number of primary coil turnings, or number of secondary coil turnings is lesser than number of primary coil turnings, then when Ns is greater, Vs is greater, so we can say that voltage of the secondary coil is greater than Vp, voltage of the primary coil, which means to say that the current decreases, current Is, Vs, this is secondary's voltage, secondary coil's turnings, secondary coil's current. Current is inversely proportional to number of turnings as well as voltage. Inversely means when Vs increases, that is here Ns is said to be increased. So here Vs is also increased, which means to say the current Is is decreased here. Okay, when in case of step down, so here we are talking about step up, which means to say step up is with respect to the voltage itself, it's not with the current. Stepping up in the sense current is reducing, stepping up in the sense voltage is increasing there. Okay, so step up in case of the inductor here you had considered, which means to say when this coil is increased with the number of turnings, the voltage in this also increases, which means to say from limited voltage to a higher voltage, stepping up. Okay, so because of which you can say that step up only in case of voltage, but the current reduces. So here in step down, it is NS is very much less, the number of turnings is very much less than that of the primary coil. So what happens when it is less? So here it says that secondary coil turnings is decreased, which means to say voltage also decreases, so Vs also decreases. These things are not necessary, it is only for your reference I'm actually doing it, but the necessary things are this as well as this. So when this decreases, number of secondary coils turning decreases, the voltage around it also decreases, which means to say that the current in the turnings increases, ulta of this. Okay, so Is increases over here. So these are the concepts what you have to remember, which means to say in step down case, the number of turnings of the primary coil is more, the number of turnings of the secondary coil is less. And at this case, it's like it is decreased, voltage also decreases, the current increases over here, which means to say the voltage is from top to bottom, it is reducing. That is why it is called as stepping down. Okay, step down, that is step up. So step up and step down transformers are very important for you to give the conditions, because of which you need to know the equations, and this is the very main equations what you have to know in order to give the step up as well as step down performance of a transformer. But in case of transformer is the one which is used to give a desired values of the alternating voltage, right? Is it like 100% efficient? No. This condition was only taken if it is 100% efficient, but no system in this universe can be called as 100% efficient, because the energy will be lost in the form of heat energy and all. Okay, so energy loss in transformers is given, and energy loss can be done with respect to the wastage of the heat energy. Okay, so out of which one of the energy is said to be hysteresis loss. Hysteresis loss in the sense, in case of hysteresis loop, what we had actually discussed in our previous classes, it was like regular magnetizing and demagnetizing of a sample. During this magnetization and demagnetization, certain amount of energy is being released, energy is being spent, because of which there is hysteresis loss, and because of which you can say that the transformer is not 100% efficient, for which in order to minimize it, what is that we have to do? We have to minimize the loop's width. That will be the one of the first loss. And next, energy loss in transformers can be done with a flux leakage. So this flux leakage can happen only when there is no proper designing, that is poor designing of a transformer can lead to the flux leakage. And then it is the third point can be given as, the third energy loss in the transformer is given as loss due to resistance which is present in the windings. Okay, when the windings of that is a conducting wire, there is some certain resistance which has been there, and due to that resistance, as we had discussed, when the resistance is connected to a AC source, due to the charges which is flowing alternatively through the resistance, the heat is being released, that is heat energy is being dissipated, and because of that the loss due to resistance is being followed, that is energy loss in transformers. And final loss is due to eddy current. So these losses are very important question in case of this chapter, alternating currents under the transformer, as well as step up as well as step down. Step up, step down, and the energy loss in case of the transformers are very important. So these four are the loss. In case of loss due to eddy current, there is heat loss which is being produced. Okay, so these are the four most important energy loss in case of this transformer. In today's class, we have dealt with the sharpness of the resonance, quality factor, frequencies, and the bandwidth and the half power frequencies, all these things, along with the resonance, what exactly is the resonance value, and the power in the AC circuit formula in order to solve the numericals, as well as the introduction on transformers, what is meant by transformers, and what are the sequences of this step up as well as step down transformers, and finally the energy loss in case of the transformers, which leads to not 100% efficient transformers. Okay, so that's all for today. Let us all meet in our next class with the upcoming new chapter. Until then, have a good day. Thank you.